inshallah today I will present my paper titled Comparative Analysis of Line Stability Indexes for Dynamic Voltage Stability. I am Fadi Al-Batsh, Senior Lecturer at University Kuala Lumpur, British Malaysian Institute. Can't make it official. Okay, the outline of my presentation, I will introduce first about what is the problem of voltage instability, and then I will introduce 4 line stability indexes, followed by the methodology used to analyze the voltage stability indexes based on dynamic analysis. Then I will show some simulation and results, and last conclusion and future works. Actually, as a result of the continuous advancement in our modern life, the power demand is keeping increasing more and more. And as a consequence of these increasing demands, the power system networks suffering from different problems, such as voltage instability, frequency instability, line overloaded, and power system blackouts. To come out with a solution for these serious problems in power system network, we have actually 2 solutions. The conventional solution is to build new power system plants and new transmission lines to supply the increasing demands, increasing electricity demands. However, this solution is very difficult to implement. Why? Because we have many challenges to implement such solutions, such as limited energy resources, deregulated electricity market, environmental constraints, time and capital to implement such a big projects. While the alternative solution is to enhance and improve the existing power system network by integrating some compensators or renewable energy resources with the existing power system network to increase the capability of the current network and improve the power quality of the whole network. To implement this solution, which is, I actually say this is the intelligent solution, we have actually one problem. The problem is where I should support the current network. Let's say we have like a large network, like for example 118 bus large network, and we decide to use this creative solution and support this network. Now the critical question, where, at which bus I should support this network? This is the main challenge actually we face. So the answer, we're supposed to support the weakest buses in this large network. Okay, how we can find and determine the weakest buses in this large network? We have actually to use line stability indexes to do analysis for the whole network and find and determine the weakest buses along all this large network. Then we can integrate our proposed solutions such as renewable energy, fax devices, compensation devices, active power filter, and so on. Okay, now I will introduce what is the line stability indexes. So actually, line stability indexes is used to do analysis for the whole network and find where is the weakest buses in terms of voltage instability. We have different and many line stability indexes. In this paper, I have presented 4 of them. Actually, the well-known indexes, which are fast voltage stability index, LQP index, voltage collapse point indicators, last LMN index. So basically, how we can use those indexes? First, you have to build your network using dynamic simulation software. for example, PSCAD or any other software. So you have to build the system, then you have to actually analyze the whole network in terms of, at each bus, I need to find the whole parameters such as VS, Q, P, theta, voltage, Z, and so on. Means we have to build the network full. At each bus, I have to measure and find all parameters of this bus. Then, using these equations, for each bus, I have to find the values of all these indexes. Means actually, I have done the analysis, and I have one Excel file. So in that Excel file, I key in the values of all parameters: voltage, current, impedance, active power, reactive power, and so on. Then automatically, I include this equation in the Excel. Automatically, we will find the value. Now, the value must be between 0 and 1. Between 0 and 1. If the index value reach 1, means this bus reached to instability condition. So this is how we use actually voltage stability indexes to find the weakest buses. We do full analysis, apply the equation, find the value of index, then analyze the values itself. If the value reach 1, means this specific bus reached to instability condition. So this is the methodology. We start by building the board system network in PSCAD. In my paper, I have used PSCAD. Then apply 4 voltage stability indexes for each transmission line from PSCAD library control blocks. We have directly tools that can measure all parameters. Then we start simulation. Then at each second, I have to check if the index is less than or equal 1 or not. If the index is actually less than 1, then I have to increase the BQ load. Why? Because I couldn't know where is the weakest buses, because none of the index exceed 1, the value 1. So in this case, what you have to do, you have to increase the BQ load for all buses. Then you do again the analysis until one of the line exceed value 1. Then we know this is the weakest buses. Now, if from the analysis the value reach 1, stop the simulation, identify the highest index value, then this will be the weakest buses. This will be actually the procedure for all buses. So in this paper, I have done 2 case studies only. One case study by increasing PQ load, one case study by increasing Q load. Now, why actually I implement these 2 case studies? Someone will ask me why you use 2 different load categories. The answer, because to find the weakest buses, you have to increase the load, yes, but the category or the pattern of the load, you have to decide based on the area. Means, if we are in industrial area, we know that the Q is high. We know that the Q is high, so we have to increase the Q load. If we are in residential area, we know that the pattern of the load BQ load. P and Q almost balanced, so we increase BQ load. You will see that the weakest buses in each case is different. However, it's in the closed area. So the analysis of this case study will come out with one line as a weakest buses, and this one will come out with another and different line. Let's see together. So first, as I mentioned in the methodology, I will do analysis for the whole network before we increase any load. I have done the analysis. I found that all indexes, all 4 of them actually, less than 1. Look here, is the highest value almost 0.25. That means none of them exceed number 1. Now we have to increase the load. Okay, so I have actually divide the network for 3 regions or 3 categories. So in this first category, we increase the load by 30%. Why? Because these lines has the lowest load. If you look here, 7, 11, 9, 3, and so on. But if you look for the category number 2, where I increase 25%, the load is higher, 21, 94. That's why I cannot increase with the same percentage because it will be overloaded. So look, for example, here, the load is also very high. That's why we increase with another less percentage. So it's not same actually. We increase with different percentages based on the current load for all buses. So after we increase, here we come up with this is the new amount. Then we will do analysis for the voltage stability indexes. Now, I have increased the load how many times? 5 times. At the first increment, still the indexes reach only 0.4. Still none of them exceed 1. So you have to increase again with the same percentage. Increase again, 0.6. Again, 0.8. Then at the 5th increasing, okay, the indexes, one of them actually reached to number 1. This is very important as a comparison between all these indexes. We know that the response of all these indexes is not similar. So for us, actually, the important is to find the fastest index that will detect where is the weakest bus early. So if you look here, we found that this index actually, VCBI, look here, can detect the weakest buses very early compared to other indexes, VCBI. After the increment, we do the full analysis. We found that the critical bus, based on the index values, is line 914. Now this is the second case study, increasing Q. So the same, okay, I will not go through deeply. We categorize different percentages, okay? Increase, till here we increase till 5 steps, okay? Same, we analyze, we found same actually, VCBI is the fastest, all right? And then we found that the critical bus in this case study is line 1340. So this is actually how we perform dynamic analysis for voltage stability indexes to find the weakest buses in the power system network. Finally, this is just a comparison between all indexes in terms of how many steps and in terms of the percentage of the increment. So we found that VCBI reached the first one after almost 150% increment. And here we found that we need only 5 steps in BQ load and 4 steps in Q load to reach or to detect the weakest buses compared to other indexes which require sometimes 6, sometimes 7 steps. Here we found that VCBI is actually the best in terms of the performance. And this is finally the conclusion. So we can find that clearly using the dynamic load increment for PQ and Q, we can find the weakest buses, and they are different based on the load pattern. And then actually from the table, we can find from the results obtained from the simulation, we found that VCBI index is more effective compared to other stability indexes. For future work, voltage stability indexes could be incorporated with other smart optimization techniques for online voltage stability assessment to reduce computational time and increase the accuracy. So this is as a future work, we need to apply some optimization techniques in order to reduce the computational time, which is very high, and in order to increase the accuracy of the measurement. And this is some references. That's all. Thank you very much. Any question?